several different ways. And finally, one last example I want to share. You're all aware of yellow fever virus? Yes? Vector-borne disease transmitted by mosquitoes. Sylvatic cycles or wild cycles of yellow fever circulate in intact forested areas. There's specific mosquito species in the forest canopy that transmit yellow fever amongst monkeys and other wildlife populations. Okay, and then there's an urban cycle where different species of mosquitoes will transmit yellow fever between people. Okay, some of these monkey species in Brazil and South America where yellow fever is endemic, howler monkeys are exquisitely sensitive to yellow fever, just like people. Okay, howler monkeys are infected with yellow fever virus. A high proportion of those infected die very quickly. Okay, so quite cleverly, thank you, quite cleverly, a One Health group of field epidemiologists. Okay, so field epidemiologists, veterinarians, doctors, nurses, people with an MPH working as a team, recognize that howler monkeys in Brazil are sentinels. Okay, they're serving as sentinels for human populations because they're exquisitely sensitive, and if they become infected with yellow fever, a high proportion die. So they set up an active surveillance system using howler monkeys as sentinels and informed the local populations in areas at risk for yellow fever. If you see sick or dead howler monkeys, call us immediately. Okay, so the communities do that. Teams go out and collect post-mortem samples from the howler monkeys and test them for yellow fever. If they find yellow fever positive howler monkeys, they then immediately do a ring vaccination program in people to protect human health. So this is also a recent publication. It's an excellent example of a One Health approach to an infectious disease that affects both wildlife and people, and using wildlife as sentinels as part of an active surveillance program to inform public health decisions. Okay? So using surveillance for yellow fever as a tool for prioritizing where to vaccinate human populations. Pretty cool. So that's all I have for the talking at you this morning. Okay, we're about 10 minutes to lunch. Yay, 10 minutes to lunch, everybody's favorite. Okay, after lunch, actually we can probably do it now. I'd like to assign, sorry. Okay, so what we're gonna do now, if you look in your modules that you were given, there's 4 different infectious diseases that are listed. Okay, so each team is gonna be assigned a disease, okay, either rabies, Streptococcus suis, leptospirosis, or dengue. So there's 8 groups. There's going to be 2 teams that are going to work on the same pathogen to develop an infectious disease management plan. Okay, so you're going to discuss in your teams after lunch. You can discuss over lunch if you want, but feel free to take a break, not do it till after lunch. And then towards the end of the session, I think the instructions in the manual say to prepare a PowerPoint presentation that you're going to present to the group. We're not going to do that. We're going to have you just debrief with the other group working on the same pathogen as you to see what the similarities and differences are in the plans that you came up with. What I want to encourage you to do as you're thinking about and developing your infectious disease management plans is to take into account what you've already been learning and experiencing this week. Okay, so what was the last session about just before this one? Culture and beliefs, values and ethics, okay? Such an incredibly important component and important influencer when you're trying to control or respond to an infectious disease outbreak, okay? A lot of infectious disease outbreaks can be managed by changing human behavior, but changing human behavior is one of the hardest things to do on the planet. It is easier to go to the moon in a rocket ship than it is to change human behavior across a wide range of communities, okay? I promise you that is true. One of the hardest things to change. So you're going to be working on some diseases that could be very easily controlled through changes of human behavior, so take those things into account. So there's lists of questions for you to consider, and your facilitators will help you work through this, and others of us will be circulating as well to help you through this. So we're going to have folks assign an infectious disease to each group, and then you'll have a few minutes to start talking about it before lunch break. Any questions? I'll look up the number and I'll tell you after lunch because I don't want to lie to you. But yes, humans and chimps are very closely related. That means it's easy in a lot of ways for pathogens to move between us. Our body temperatures are the same. We're primates. There's a lot of similarities in our binding sites and receptors and metabolism and biochemistry. So it's easy for the pathogens or potential pathogens to move back and forth. You said that, you know, the first time a pathogen is shared, it's not going to cause a problem. That's not necessarily true. Okay? The first time a pathogen moves between species, it might cause a terrible problem. Okay? So relying on that, you know, oh, it's just the first time, it's not going to be a problem. That's not the case. Okay? The first time a movement occurs, it can be very bad. What I said is that every time a movement occurs, that's another opportunity. It's another challenge for a pathogen to adapt. Okay, so I can give an example. Recent, in geological time, recent disease emergence. HIV, which many of you may not consider a recent disease, but I remember when it emerged because I'm really old. So HIV emerged into the human species from chimpanzees. Okay, from one called simian immunodeficiency virus variants in chimpanzees. Okay, so SIV chimpanzee had multiple opportunities to spill over into the human populations from people hunting and consuming chimpanzees as bushmeat in several different countries and places in West Africa and Central Africa. There are several different strains of HIV. You're aware of that, right? HIV-1, HIV-2. Those strains, the different strains of HIV, evolved from different spillover events of different strains of SIV chimpanzee. Okay? Now, virologists who study that kind of thing call it viral chatter or viral spillover, that where these interfaces where this viral spillover is happening, it probably happens hundreds or thousands of times that a pathogen moves from one species to another, from chimpanzees into people. But it doesn't get a foothold, right? It doesn't catch on, it doesn't adapt every time. But keep giving a pathogen or potential pathogen an opportunity to adapt to a new host, and it's probably only a matter of time, right? If that spillover can occur, it's probably just a matter of time with enough exposures, enough opportunities. That might be millions of time, it might take thousands of years or more, but every time that that contact and that exchange happens is an opportunity for adaptation. So we would like to reduce those opportunities for adaptation. Does that make sense? We call it, if you're doing it in a lab, you call it a passage or a passage if you speak French, right? So when you put a virus into a cell culture, right, and you're looking for viral mutation rates, every time you introduce the virus into one cell culture, that's called a passage, right? And you can look and see how much a virus can adapt and mutate in one passage in a particular cell culture, in 2, in 3, in 4. Okay, so we know that from laboratory work, that every time a virus has an opportunity to replicate in a new cell, that's a chance for that virus to change and become better adapted to that cell. That's what I meant. Any other questions? Yes.
Yeah, thank you for the opportunity. So I want to ask something related to vaccine actually. So I have learned and studied a bit that there is this technique of making vaccine called attenuation, in which where we can grow virus into another host, making it more adaptable into that host, and then finally we can take the virus back from that host into our body, which our body will become more, that host, that agent will become less adaptable to our body, and our body will create a better immune response towards that host, towards that agent, because the agent is less adaptable to our body. What I want to ask is it really possible that it can also occur naturally? Like you said that agents can cross from one host to another and then back to another host, right? So can it also occur that way? I mean, if, for example, we are infected with virus A, and then at one event, that virus, all of the virus A has been removed from our population and moved to chimpanzees, for example. And then in one event, that virus is already adaptable to chimpanzees more than our body, and then in one event, it moves again to our body. Will it be possible if our body becomes more stronger than to that virus?
Yeah, so the question is about viral attenuation and, you know, how pathogens adapt. Sometimes they become, attenuation means weakening, right? Sometimes they become weaker That's shorthand for changing a pathogen, a virus, a bacteria, so that it is not causing such severe disease or such severe disease in the majority of the population. And I qualify that because I'm going to give you an example of attenuation in just a minute. So, and the question is whether that can happen if it always happens, right? That it's attenuation, that it's weakening, or sometimes pathogens can become more virulent. They can become stronger. So adaptation doesn't just go in one direction, right? Just like pathogens don't only move in one direction. So adaptation, we end up with different strains of bacteria, of viruses, right? They have opportunities to adapt, to be challenged in new environments. So we end up with different strains. Some are, we know that from many different types of pathogens. Some strains of some pathogens are more virulent, cause worse effects when infected than others, right? Some are avirulent. So there's no guaranteeing that direction when it's happening in a natural system. And the example that I like to use with live attenuated virus vaccines, they can be very effective, very immunogenic. And poliovirus is a very good example of a live attenuated viral vaccine that's been used to help almost eradicate polio globally, right? So how many human pathogens have been eradicated? Somebody said 2, huh? Yeah. How many human pathogens have been eradicated? Anybody want to confidently say a number? Okay, there's only one human pathogen that's been eradicated globally. Do you know what it is? Smallpox. You guys know it, okay? Smallpox, okay? So my generation, we were still vaccinated for smallpox. I have the smallpox vaccine scar. Pretty much everybody younger than me has not been vaccinated for smallpox because it's been eradicated. Smallpox virus, live virus, still exists in laboratories, frozen in ultra cold, right? Maybe in the thawing tundra of Siberia, we don't know yet. Something to keep your eyes on. Okay. But poliovirus and several other pathogens, guinea worm, are close to being eradicated. Yeah, and the live poliovirus vaccine has been one of the major components of that eradication because it's live, it's very immunogenic, and it also, when you're infected with a live virus, if that virus replicates in your body and finds a portal of exit, which the live poliovirus vaccine can do, it's sort of secondary vaccination of others in the community. You don't have to vaccinate every single person in a community with live poliovirus vaccine because through urine and feces, others are going to be exposed to that virus. However, what happens in a very few cases now is that there's live poliovirus reversion to virulence, or in particular people, genetic susceptibilities, immunocompromise, other variables and criteria that live poliovirus that is safe for the majority of the human population can cause flaccid paralysis, polio disease in a small percentage of the population. And so now, because the eradication campaigns have been so successful, there are actually more cases of flaccid paralysis caused by giving live poliovirus vaccine than there are by wild poliovirus strains. So a lot of the vaccine, the extended program for immunization of WHO has switched to killed poliovirus injections. Does that make sense as an example? So